So hello everyone. Today I will share our new paper, Knowledge Enhancement for Multi-Behavior Contrastive Recommendation with you. I'm the reporter Xuan Hongrui, a graduate student from Nanjing University of Aeronautics and Astronautics. And this is the contents of our paper. I will share from the following aspects. And now I will introduce the background of this work. So why should we study the multi-behavior recommendation? As we all know, traditional recommendations always assume that only a single type of behaviors between user and item. But in real world, there are many types of behaviors between user and item. So as we can see, in shopping online, people can add items to the shopping cart, to the favorite, or buy. So in fact, the traditional methods are no longer in line with recommendation requirements in complex situations. So more and more research have to study the multi-behavior recommendation. And as the emerging direction of recommendation, multi-behavior recommendation has faced two limitations in practical research. One is individualized behavior's diversity. It is shown on two aspects. One, the dependencies between different behaviors is complex. And the relationship between some behaviors may be positive for recommendation, and the others may not be that. Then, this dependencies varies from user to user. This is easy to understand because everyone has different behavioral preferences. So, how building an efficient transfer way to get the sufficient behavioral partners is crucial. And then, the other limitation is the targeted behavioral data sparsity. And as we all know, recommendation methods always use supervised information for learning and training. So it is essential to have the targeted behavioral data. But unfortunately, in real world, the interactions observed under targeted behavior are often sparser compared to other interactions. It is obvious that the data of people approaching online is much lower than the data of clicks. And as we can see in the pictures, the targeted behavioral data is always sparser than other interactions. So, how to deal with individualized behavior's diversity? The key of it is to capture the dependencies between behaviors and distinguish differences between users. And in views of success in CV and NLP, many work use CL to distinguish the similarities and differences for user and item in recommendation. And we can see the work CML introduce the CL into the multi-behavior recommendation and achieve some result. So we find that CL is very suited to explore the cross-grain communities between behaviors and fine-grained differences between users. And then, how to deal with targeted behavioral data sparsity? The key of it is the knowledge graph, because we think that the multi-behavioral information is an enhancement of information on the user side. So an naive idea is to apply the KG as an enhancement way from the item side. And it is also used by many works, like KJGT and KHJT. So we want to combine the user side information and item side information to get better user preferences. And this is the definition and formulation of our paper. And we can notice that the inputs of our work is GU and GV. And we want to get a function. It can infer the interaction probability Y of user I and item G under the key type behavior. And this is some details about GU and GV. And now I will introduce the overview of our methods, KMCR. In our methods, we will put the graph GU into the multi-behavior learning module and put the GV into the knowledge enhancement module to get the different embeddings of VU and VI. Then we combine the embedding and put them into the joint learning module for learning and training. And this is the overview chart of our KMCR in our paper. We also call the three modules as KEM, GLM, and BLM. So now let's look at the BLM, multi-behavior learning module. In this module, we have Goal 1 and Goal 2. In Goal 1, inspired by LegGCN, we construct a single behavioral embeddings through the encoder. And then we perform scroll-type behavioral embedding aggregation to preserve the different behavioral information. And then in Goal 2, we hope to construct different views and regard them as auxiliary signals to alleviate the data sparsity. So, we treat different behaviors as views and perform CL to minimize the differences between behaviors of the same user A and maximize the gap between user A and user B. And then is a KEM, the knowledge enhancement module. In this module, we also have Goal 1 and Goal 2. And in Goal 1, we propose a way of aggregating the neighbors by attention weight to reflect the different importance of neighbors in KG. And then we use TransR and TATC to focus on the rationality and the potential semantics of triples in KG to get different views, GK1 and GK2. And so the KG is benefit for recommendation. It also introduces some noise. So inspired by this point, we set different seed to sample from the GK1 and GK2 and compute the similarity to get the score of the C. So generally speaking, the more stable of a node, the higher the score of C. Then, to reflect the user preferences, we adjust the score from the user view and want to use A to guide the selection of edges in target behavior interaction graph. And here, POI is the initial selection probability. Then we perform its min-max normalization function to transform POI into the interval A to B to get the final probability. So in this case, we get two interaction subgraphs, GU1 and GU2. And now, KMCR obtains two pairs of graphs with different information, GK1, GU1, GK2, GU2. And begin with the motivation of Goal2 in BLM, we also use CL to string the item size information from the KG. And up to now, we also reduce the impact of noise and alleviate the issue of data sparsity. So now, we get two types of embeddings for user and item. One use multi-behavior information, and the other use the KG information. And then we set weight alpha to combine them. And it should be noticed that we use the BPR loss as the mean task loss and propose a training paradigm to better learn the information from different views. And the paradigm is that at the beginning, we will train the two cell tasks in their own spaces. And then the two-part trained embeddings are combined with the weight alpha. We calculate the mean model's BPR loss and CL loss for the new embeddings. And please notice that the mean model is like GCN in BLM. And now it's experiments. We use the data side in table 1. It includes YERP, Camel, and Rita. Oh, sorry. And we also compare our methods with the baselines on screen. They are from different research labs. And we show all the results in table 2. So we can get that KMCR achieves the best performance on each data site to confirm the effectiveness and generality of our method. And we also can see that the methods of introducing auxiliary information are always better than the traditional information. And then CLML is usually the one with the best performance in all baselines. So it proves that CL is beneficial for the capture of user preferences among different behaviors. And then we explore the impact of different components and show them in table 3. So we set WMCL to study the influence of the multi-behavior information, and set WKCL to study that the introduction of KG is beneficial to enhance the item size information. And then set W0T to verify the effective of our joint training paradigm. And all the results in table 3 shows their effectiveness. And then we verify KMCR on date with different degrees of sparsity in finger 2. And we also can find that, compared with other methods, KMCR performs consistently when dealing with the data with different degrees of sparsity. And then the performance gap between our approach and other methods becomes more significant with data becomes sparser. And as we all know, whether in multi-behavior graph and KG, there are some noise. So I try to use some method to reduce the impact of them. So for multi-behavior graph, we set a series of dropout and explore the best value under different day size. And then by adjusting the interval A to B, KMCR realized the noise reduction of Kg. And please attention, we use the interval to reflect the tolerance of KMCR to the noise. So finally, its conclusion. And in this work, we propose a framework KMCR for recommendation, which enhances the information from the user side and item side, solving the issue of targeted behavior data sparsity. And then we propose 2CL task and a loss paradigm, which can better explore the cross-grain communities between behaviors and fine-grained differences between users to improve the recommendation performance. And then we conduct experiments on 3 real-world data sites to show that our work outperforms compared with other state-of-the-art methods. So that's all. Thank you.